Hi, this is Jason with Liquid Instruments. This is the first video in a three-part series about encoding, converting, and decoding digital data using different instruments available on Moku devices. Today I'm going to show you how the Moku pattern generator can be used to encode digital data. We're going to be working in multi-instrument mode, so select that from the main screen. We're going to put the logic analyzer in slot 1 and the oscilloscope in slot 2 so we can view the output. We don't need to make any changes to the connection map, so click Apply Changes and wait for the FPGA to configure. Open the window for the logic analyzer. Now, there are two main sections to this instrument: the logic analyzer, which you can see in front of you right now, and the pattern generator. We're going to be primarily using the pattern generator today, which you can access by clicking on this button in the bottom right. Using this screen, you can enable and configure the output of one or both of the pattern generators, which correspond to the two outputs from the instrument slot that we saw in the previous screen. Now let me explain the settings for this instrument. On the right, you can see a preview of the output with a timescale along the bottom. This timescale is determined by the base frequency, the baud rate, and the number of ticks. While the base frequency for the Moku Go is fixed at 125 MHz, the divider or baud rate can be adjusted to fix the resolution. These two values are inversely proportional. Increasing one will cause the other to decrease. So if I set the baud rate to 10,000, you can see that the divider jumps up to 12,500. We'll set the divider to be 1250, which corresponds to a time resolution of 10 microseconds. The number of ticks then determines the total length of the sequence. 10 ticks of 10 microseconds will be 100 microseconds, as you can see on the bottom. If I increase this to 100, you can see that it goes to 1 millisecond. But let's stay at 10. The patterns are built using 16-bit signed integers, meaning that bits 0 through 14 determine the absolute value of the output, while bit 15 determines the sign. The output is scaled to have a maximum of plus or minus 5 volts, and the maximum positive voltage will correspond to bits 0 to 14, all being 1, and bit 15 being 0, and the maximum negative voltage will correspond to bits 0 through 14, all being 0, and bit 15 being 1. Click Edit Pattern to pull up the editor. From here you have the option to set the bitstream values for each tick in the cycle. Earlier we set this value to be 10 ticks, so you see 0 through 9 at the top. Now we're going to set a clock pulse on bit 13, so click Fill With, Clock, and Fill. And then we'll add another bit onto the last pulse. So bit 12, we're going to add a bit on top. So every fifth pulse is going to be a little bit higher amplitude than the previous 4. Let's close this window. We can see the preview. Now let's close out of the logic analyzer and return to the configuration screen. Click over to the oscilloscope window. If we enable channel A and disable channel B and autoscale, we can see the pulse pattern that we programmed. And you can use the scope to confirm that our pattern is repeating. Adjusting the trigger, we can show that it is indeed repeating every 100 microseconds. If you look at the time scale down at the bottom, we can see that indeed every fifth pulse has a little bit higher amplitude than the previous 4. So that's all for today. In the next video, we'll talk about how to encode this pulse sequence using analog modulation techniques such as amplitude shift keying. Thank you, and see you next time.